Thanks for watching Edupedia World videos. In this video we begin a new unit of semiconductors and we start with the discussion of energy bands present in various types of solids. Most of the things we'll see in this video are derived from one simple equation, J is equal to sigma E. This is called Ohm's law and we've seen this before. The more familiar version of Ohm's law is V is equal to IR, but we've already seen how that can be derived from J is equal to sigma E. Sigma is called the conductivity of the material. Now, based on the range of conductivity, we classify solids into three different types. The first is conductors, and in that sigma is very high, which means the conductivity is high. Any small electric field will give rise to a large current density, which basically means any small potential difference will give rise to a large amount of current. Then you have on the other extreme insulators, in which sigma is almost zero, it is negligible. And then the third category of materials has a conductivity which is in between conductors and insulators, and so they are aptly named semiconductors. And they have sigma which is greater than 0 but is less than the sigma of conductors. Another difference, and we'll see the reasons for that in a later video, is that for conductors sigma decreases as temperature increases. This is because as temperature increases, the average lifetime between collisions decreases, which means that the electrons have a smaller and smaller time to gain appreciable velocity and give rise to a current density. On the other hand, for semiconductors, the conductivity increases as temperature increases. So these are the two major differences between conductors and semiconductors, and the explanation for these differences comes in the form of energy bands. Now, we've used the term energy states before when we were talking about atoms, but we haven't really talked about energy bands. So let's look at for a second solid sodium. We have a chunk of solid sodium, Na, which has an electronic configuration of 1s2, 2s2, 2p6, 3s1. Right. Which means the first n is equal to 1 shell is completely filled, n is equal to 2 shell is completely filled, but the n is equal to 3 shell is partially filled. Let's assume we have n sodium atoms. And let's for a second assume that they're not solid. Let's for a second assume that we have a sodium vapor. If we have a sodium vapor, that means the sodium atoms are well separated, so they don't really interact with each other. N is a very large number of the order of Avogadro's constant, and in that case we would have different energy levels and electrons would populate them in different numbers. So the 1s energy state, because there are n sodium atoms and each sodium atom can have 2 electrons in its 1s energy state, the 1s energy state will have a total of 2n available states, and out of them 2n or all of them will be filled. This is the energy level. This is the number of available states. And this is the total number of occupied states. Since the 1s energy level can have a total of 2 electrons, when you have n sodium atoms, you have total 2n available states in the 1s energy level, and they are occupied by the 2n atoms. Similarly, the 2s energy level can have a total of 2n available states, and all of them will be occupied. The 2p energy level has a total of 6n energy states, because there are 6 electrons that can be there in the 2p shell. The 2p, by the way, is n is equal to 2, L is equal to 1. We've seen that in Bohr's model. And all 6n of these are filled. So for the first three energy states, they're completely filled, but when we move on to 3s, the things get interesting. For 3s, there are a total of 2n energy states, but only n of them are filled. Because the 3s state can occupy a total of 2 electrons, but we only have 1 electron in 3s state in the sodium atom. Then you have 3p. I'll not go any further. 3p can have a total of 6n states, but it really has no electrons in any of these. Now, this is in sodium vapor, where each and every atom is well separated from the other atom, so they don't interact, and every energy level has a discrete value of energy. This might be 1s, this might be 2s, 2p, 3s, and so on. But when you start bringing them together, that means when you start talking about a solid as opposed to a vapor, then these energy levels start interacting. They might even move up and down a little bit, and in that case, the energy states, which would be a single line, become energy bands. So instead of 1s, 2s, 2p and 3s, we could have something like this would be the 1s, this would be the 1s band, this would be the 2s band. So initially this was the level of the 1s energy state, because all the atoms were well separated. When they start interacting with each other, the energies might change by slight amounts. So instead of being at this average level, this would be the 1s energy band. So that is where the concept of energy bands as it regards to solids comes from. The different energy states interact a little bit with each other, and they give rise to a wider spread in energy for any energy level, and these are called energy bands. Now at 0 Kelvin, the energy is the lowest and the bands are filled from top to bottom according to Pauli's exclusion principle. So first all the 1s states will be filled. Then once the 1s states are completely filled, any new electron will go into the 2s state, and then we'll slowly fill the 2s states and we'll move up and so on. But as we increase the temperature, electrons exchange energy with each other in the ions. So in that case, it's not necessarily true that all the electrons will be occupying the lowest energy state. Now the difference between the lowest energy in a high energy level and the highest energy in the next lower energy level, this difference is called the band gap between the bands. So the difference between the energy level of the lowest state of the higher one and of the highest state of the lower one is called the band gap. There are two types of energy bands available, and they are decided by whether or not they are filled at 0 Kelvin. Remember, 0 Kelvin is the only temperature when you actually have energy going from the lowest to the highest states in order. So the energy bands, I'll just call them EB for now, energy bands that are completely filled at 0 Kelvin are called valence bands, and we'll denote them by VB. Now generally the highest energy state that is completely filled is called the valence band, but we generally call valence band any of these, though when we'll be talking about valence bands, the band that will be of interest will be the highest energy one. Then you have the other type of bands, the bands with energies, the bands with energies higher than the valence band are called conduction bands. And we'll refer to them as CB. So generally, let's say we have one band, then we have a second band, we have a third band, and a fourth band, and this is completely filled, this is completely filled, but this one is partially filled, not completely filled. Let's say half filled. Then these two would be the valence bands, and this one and any one above this will be the conduction bands. Now again, generally the interest to us is of these two bands. So generally the valence band means the highest valence band, and generally by the conduction band we are referring to the lowest conduction band. Though technically all higher bands will also fall under the category of conduction bands. Now let's try to distinguish the types of materials, semiconductors, conductors and insulators, based on the band structure they have. So let's look at conductors first. There are two possible band configurations which a conductor could have. The first one is the one which we just saw right now. I'll try to draw the figures a little bit clearer now. The width doesn't matter. So this is the lowest one that's completely filled. This is completely filled. And this is half filled. In that case, when we say valence band, we mean these both, but generally we'll be talking about this one, and this will be the conduction band. So this is the case for conductors, in which the conduction band is the highest occupied energy band, and that is only partially filled at 0 Kelvin. Right. This is generally true if the outermost subshell has an odd number of electrons, like we saw in the case of sodium, where we had 1s2, 2s2, 2p6, 3s1. So the first three would be valence bands, and the fourth one, the 3s1, would be the conduction band, and it's only half filled. In that case, what can happen is electrons can move within the conduction band from one atom to another. Right. So an analog of that would be something like, if this is the sodium atom, I'll just draw the two outermost shells right now. So this one would have, let's say, a total of 6 electrons, and this one would have 1 electron, and another sodium atom, nearby sodium atom, would have 1 electron here as well, and this electron could actually jump and go into the energy into this atom, but it will still be in this band because this is the 3s energy band. So because the conduction band, the lowest conduction band, is partially filled, you can actually have free movement of electrons, which is the reason they are conductors, because they can transmit electricity quite easily. Now this is not the only way you can have conductors. This is a way you can have conductors of the type of sodium, which have partially filled shells, but there is also another way you can have conduction, and that is in atoms like zinc, which have a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s2. So we see that in this case the 4s2 shell, or the outermost shell, is completely filled, right? And in this case the bands might look something like this. So this is completely filled. This would be the 3d10. This is completely filled, and this would be the 4s2. This would be the 4p, and this would be the 4d. So in zinc what happens is, yes, the outermost shell, the 4s shell, is completely filled, but the energy levels of the 4s and 4p shells actually overlap. We talked about in Bohr's model that the energy technically for hydrogen-like atoms only depends on N, but as you start increasing the number of electrons, it depends on both N and L. However, for the case of zinc, 4p and 4s have actually quite nearby energies, so when you have a large number of electrons of atoms interacting with each other, the energy bands are created such that they overlap. So it's not exactly the same as this where you have a partial energy shell, but still, because the energy between these two, the energy difference is very small, you could easily have an electron from the 4s shell going into the 4p shell of another electron. The way to show this would be something like this. Let's say you have 10 electrons here. This is the 3d10, and then you have 2 electrons here. the 4s, the same goes in another nearby atom. But the 4p shell does not have an energy that is very much larger than the 4s shell. It actually sort of overlaps with the 4s shell. So this is the 4p shell that is dashed, and one electron from the 4s shell of one atom could go into the 4p shell of another atom and thus become a conducting electron. So these are the two possible ways you can have conductors. You can either have a partially filled conduction band in which the electrons can just move within this band from one atom to another, or you could have a fully filled valence band, but the conduction band that is just next to the valence band, just above the valence band, could have an energy overlapping with the valence band. In that case, an electron could easily go from the 4s shell to the 4p shell like this, and in this case also you would have lots and lots of free electrons, giving rise to a large conductivity. Now let's look at insulators for once before we go to semiconductors. In insulators, the band structure is generally something like this. Now, at a temperature T, the energy which electrons generally absorb from each other due to their interactions is of the order of kT. kT is called the thermal energy, K is the Boltzmann constant, and it is generally the order by which the temperature would change the energy. So at a temperature T, electrons generally absorb energy that is around kT. At 300 Kelvin, kT is approximately equal to 0.026 electron volts. So near room temperature, electrons generally absorb around this much energy due to their interactions with other electrons. So if the band gap between the conduction band and the valence band is much larger than this, then because of thermal energy, no electron could go from the valence band to the conduction band. So if this is the valence band that is fully filled, and this is the valence band that is fully filled, and this is the conduction band, and Eg is the band gap between these two. The band gap, if that is much greater than kT, then no electron from the valence band will ever be able to go to the conduction band. The atomic view of this would be something like this. 1, 2, 3, 4, 5, 6. So let's say you have the outermost shell completely filled, and unlike in the case of zinc, the next shell energy level has an energy much larger than this one. So the amount of energy these electrons gain from interaction with other electrons is not enough to excite them to the next energy level. In that case, you will have no free electrons and the conductivity will be very small. Now, the semiconductors are sort of like a special case of insulators in that the conduction band and valence bands, they do not overlap, and the conduction bands are not partially filled. However, just like in the case of insulators, you have a fully filled valence band and a conduction band. The difference is the conduction band is not very far above the valence band. So conductors, you had a very large number of free electrons. Insulators, you had almost no free electrons. But for semiconductors, if this is the valence band and this is the conduction band, then the energy gap between the two is approximately of the order of kT, right? For silicon, it's 1.1 electron volts, which means that electrons could actually absorb this amount of energy from each other and go from the valence band to the conduction band. This also shows us why in the case of semiconductors, conductivity increases with temperature, because as temperature increases due to interactions, more electrons would go from the valence band to the conduction band. Now, when an electron goes from the valence band to the conduction band, you have an electron present in the conduction band, but you also have a vacancy present in the valence band. These vacancies are called holes, and they sort of behave like positively charged carriers. So, in a movement of an electron from the bottom to the top could actually be seen as a movement of a hole from the top to the bottom. And the only reason we do that is because it's much more convenient to talk about positive charges than it is about negative charges. And there's another way you can actually see how these holes actually influence the conductivity. When you have solid silicon, just like in the case of carbon, it is attached by 4 covalent bonds to other silicon atoms. So these are the covalent bonds formed. Now, due to exchange of thermal energy, one covalent bond may be broken and an electron here might go. Let's assume that one of these covalent bonds was just partially completed and this was empty. In that case, this electron could actually go to this covalent bond, and then this covalent bond would be empty. So instead of saying the electron moved from this bond to this bond, we could actually say that a vacancy moved from this bond to this bond. So a movement of electrons in one direction can actually be mathematically considered equivalent to a movement of vacancies in the other direction. Right. And this is the main reason why we see that we need a separate group of semiconductors which is different from conductors or insulators, because conductors either have a partially filled conduction band, or they have a conduction band which overlaps with the valence band, whereas in insulators the band gap between conduction and valence bands is very large, so large in fact that it can never be achieved by thermal energy collisions. However, for a semiconductor, the energy it requires to break a bond and then to an electron to go from one bond to another, thus carrying current with it. Remember, current is basically just movement of electrons. The energy needed for this can be acquired by thermal energy, which is of the order of kT. So if the band gap is of the order of kT, then we get semiconductors, and of course here we can directly see as the temperature increases, the conductivity of semiconductors increases. In the next video, we'll look at semiconductors in more detail and see how by adding a few impurities we can actually drastically increase the conductivity of semiconductors. Thank you.